after getting the result for acceleration, we can do some more mathematics and get another result. Note that this acceleration is instantaneous acceleration and it won't be constant because capital M won't be constant. As more and more fuel comes out of the rocket, it becomes lighter and lighter and lighter. The capital M is changing continuously. It is dependent on time. And it falls. As time increases, it falls. And therefore acceleration rises and rises and rises. Now, if m0 was the mass at time t equal to 0, then m is given by m0 minus r times t, right? RT is the amount of gas that has left the rocket. That means dV by dt is RU over m0 minus RT. And therefore dV is RU upon m0 minus RT dt. When time is 0, how much is V? And when time is t, how much is V? When time is t, V is V. And let's say when time is 0, V is 0. When you integrate this, then R being constant comes out of the integral, U being constant comes out of the integral, integral of 1 upon m0 minus RT is this part from 0 to t. Putting t in place of t, putting 0 in place of t. Minus sign in between. Log of m0 minus RT whole upon m0. Now this minus sign can be removed by inverting what is inside the log. So we have V equal to U times log m0 upon m0 minus RT. Now here I took at t equal to 0, V equal to 0, and only then this result is valid. If at t equal to 0, V is not 0, then when you are integrating, you will take that point into account. Right? So the last result is valid when we have taken at t equal to 0, V is 0. But what we got at the top, acceleration equal to RU whole divided by capital M. That result did not assume that at t equal to 0, the speed should be 0. Right? So that is more general, you can say. And one more point. When we apply conservation of linear momentum, what we did was, after time t, we considered some delta t time. Now delta t can be a small time. So for a very small time, you can ignore external force. But in the bottom, when you are considering a long stretch of time, 0 to t, in that case, you can't ignore external force. If a bat hits a ball suddenly, then for a very small period of time, things happen. Delta t time we considered when we applied conservation of linear momentum, and then we got the result dv by dt equal to ru by m. So it was okay not to talk about external force. But when you integrate over 0 to t time, and that could be a big time also, maybe 30 minutes, what happened? Now for a 30 minutes travel, you can't ignore external force. Say for example, rocket was fired from Earth's surface. Now how can you ignore Earth's attraction for 30 minutes period? So the bottom part, the integration part of our discussion is valid when there is no gravity, there is no external force. Okay? Say in a gravity-free space, the rocket has traveled large distance and is somewhere in the universe where the effect of gravity is negligible. So this is not purely academic discussion. It may have some practical significance in such place in the universe where the effect of gravity is very small or negligible. Let's take some problems now. In case this question came to your mind that when car is driven, even then exhaust comes out. So why don't we treat car as system of variable mass? If you look at this number, it will make some sense to you. 2.3 kilogram every second. Now, thrust is what we want. Thrust is the force. We already have the result for acceleration. So the thrust is Ru. Thrust is Ru. R is given to you. U is given to you. Just put the numbers and calculate. (6440 Newton). What is the initial acceleration of the rocket? Well, that should be no problem. Acceleration at any instant is RU upon mass at that instant. So if you want A naught, initial acceleration, R is fixed, U is fixed, M naught. That's it. Initial mass is 850 kilograms. Check your working. That looks like a huge number, 805. It should be smaller, much smaller, I suppose. Seven point something. Right. Part C. You must have seen in some science movies that there is a big space ship, and from that big spaceship, smaller sized objects are launched. In part C, that's the situation we have. Rocket is launched from a spacecraft already in deep space, where we can neglect any gravitational force. This number is given without fuel. When the spacecraft leaves, when the rocket leaves the spacecraft, like bullet leaves the gun, then gun has a recoil. So strictly speaking, spacecraft will have a recoil. But assume that spacecraft is so massive that the launch does not alter its speed. So that means you can treat spacecraft as stationary. In fact, initially, with respect to the spacecraft, the rocket is at rest. So we may not need to integrate again. We can use this result directly. V equal to U times log of m naught upon m naught minus RT. Because initial speed is 0. M naught minus RT is the final mass. And for our problem, final mass is when the fuel has exhausted. U is given as 2800. Initial mass 850. Final mass 180. Just look at those numbers. Without fuel, mass is 180. And with fuel, the mass is 8. Without fuel, it is 180. And with fuel, it is 850. Most of the mass is fuel. Most of the mass is that of fuel. That's not the case in car, right? And when you calculate this, this comes out to be 4345 point something. You hear about supersonic aircrafts and look at that number. Speed of sound around 340 meters per second, and look at that. I think 4346 is somewhat better. 4346.38. So somewhere around 4300 meters per second. Now at that speed there is no fuel left. There is no fuel left. So controlling it will be very hard. According to Newton's first law, it will continue to move with that speed, 4346 meters per second. And possibly it may not have a good fit. This result is valid if at t equal to 0, v is 0. But we can't use it here. That means we need to start from here. In fact, basically, limits of integration will change. In place of 0 to v, just make it initial to final, vf and vi maybe. So vf minus vi, right side will be the same. This will become vf minus vi, right side is the same. Vf minus vi, same. Vf minus vi. So a slight modification to the result. Vf minus vi. That is u log m naught upon m naught minus RT. And since we have used m naught for mass at time t equal to 0, maybe I can use v naught for the speed at t equal to 0. And at time t, mass is capital M. So let's say at time t, velocity is just v. Vs is just v. So how about this? You want final? So to answer final, you need to know v naught. You need to know u, m naught. In fact, r and t are not given. So can you tell me what can be done for this part? Any idea? What can be done for this part? That's good. Ejecting 80 kilograms of exhaust. That means RT is 80. Just put the numbers and see what answer you get. Any questions? Let me know. Well, the answer I have is around 108. Note that we have assumed almost no effect of gravity. And also note that our frame is the sun frame relative to the sun. So your observer is located at the sun. In this particular question, part C that is, your observer was at the spacecraft. All observations are with respect to the spacecraft. Again, think about these numbers. 2.55 versus 1.8. Again, you find that more mass is that of fuel, more in comparison to the material of the rocket. Here your frame will be this frame. And look at this number also, 480 kilograms in 1 second. Mass of a small car is around 1000 kg. So in 2 seconds, nearly 1000 kg is gone, mass of a small car. Okay, try to answer part A, thrust. Thrust means mass into acceleration. Let me check. I can see some errors of zeros. Alright. If you would like this to be discussed on the board, raise your hand. Alright, then I suppose no problem with part A. Can you try part B now? Let me check. (1.35 into 10 to the power 5 kg). If you would like this to be discussed on the board, raise your hand. Fine. Here we go. See if you are getting it. Try part C also. Speed of the rocket. Let me check. Yes, 2.08 kilometer per second or 2080 meter per second. If you would like part C to be discussed on the board, raise your hand. Initially at rest, I'm not sure what exactly is your problem. You have to just put the values. Initially at rest means this formula, V equal to U, bottom of screen 1. Then U. U is 3.27 kilometer per second. So you can see how quickly exhaust gases come out with respect to the rocket. M naught 2.55 into 10 to the power 5. How much mass? M naught minus RT is how much mass is left. And I think which we have already found out in part B. So 1.35 into 10 to the power 5. Just calculate this and see if you are getting it now. System of variable mass can also mean situations different from rocket propulsion. Practically, you come across many situations where this type of thing happens, that you have system of variable mass. Imagine sand dropping on something continuously. Dropping on something, so its mass increases. But some container of sand, if you consider, having some leakage, then its mass decreases. Imagine a water tank with hole. Water drops continuously. Imagine a machine gun firing continuously small bullets. Imagine in airport you have a rotor sort of a thing in which luggage moves and luggage is being removed continuously. There may be several examples of system of variable mass besides rocket. Now let's look at this problem. Well, the answer I have is more than 100. So you will have to check your working. I hope you understand why I have written M1 minus M2 and not M2 minus M1. Because R is a positive number and final mass will be less than the initial mass. Right? That one. Now T1 is initial time, T2 is T, starting from rest, initial speed is 0, let's say final V2 is V itself, final M2 is M, let's say, M1 is M, T2 is T, no, M1 is M naught, M2 is M, final. So finally these two equations time is given to you, R you already know, force you know, M naught you know, V is what you want. Can you tell me how much would be M? Well, in fact, M can be removed from these two equations. What you need to do is, in place of M, put Ft upon V. And then you solve for V. So V is Ft upon M naught minus RT. Just put the numbers and see what answer you are getting. You are getting 120. Yes, that's the answer I have. 120 meter per second. 120 meter per second. It's like a puzzle with physics in it. Now, that's your assignment question. We stop now.